This episode is brought to you by Cisco Educational Premium. Did you know that spin is an inherent property of a quantum particle? Spin is a conserved quantity carried by elementary particles and thus by composite particles or hadrons and atomic nuclei. Spin is one of two types of angular momentum in quantum mechanics, the other being orbital angular momentum. The orbital angular momentum operator is the quantum mechanical counterpart to the classical angular momentum of orbital revolution and appears when the periodic structure to its wave function as the angle varies. For photons, spin is the quantum mechanical counterpart of the polarization of light. For electrons, the spin has no classical counterpart. The existence of electron spin angular momentum is inferred from experiments such as the Stern-Galach experiment, in which silver atoms were observed to possess two possible discrete angular momenta despite having no orbital angular momentum. The existence of the electron spin can be inferred theoretically from the spin statistics theorem and from the Pauli exclusion principle, and vice versa. Given the particular spin of the electron, one may derive the Pauli exclusion principle. Spin is described mathematically as a vector for some particles such as photons, and as spinors and pi spinors for other particles such as electrons. Spinors and bispinors behave similarly to vectors. They have definite magnitudes and change under rotations. However, they use an unconventional direction, and I quote, "All elementary particles of a given kind have the same magnitude of spin angular momentum, though its direction may change. These are indicated by assigning the particle a spin quantum number. The SI unit of spin is the same as classical angular momentum. In practice, spin is given as a dimensionless spin quantum number by dividing the spin angular momentum by the reduced Planck's constant, which has the same dimensions as angular momentum, although this is not the full computation of this value. Very often, the quantum number is simply called spin. The fact that it is a quantum number is implicit. As the name suggests, spin was originally conceived as the rotation of a particle around some axis, while the question of whether the elementary particles actually rotate is ambiguous, as they appear point-like. This picture is correct insofar as spin obeys the same mathematical laws as quantized angular momenta do. In particular, spin implies that the particle phase changes with angle. On the other hand, spin has some peculiar properties that distinguish it from orbital angular momenta. These properties are: 1. Spin quantum numbers may take half-integer values. 2. Although the direction of its spin can be changed, an elementary particle cannot be made to spin faster or slower. 3. The spin of a charged particle is associated with a magnetic dipole moment with a g factor different from 1. This could occur classically only if the internal charge of the particle were distributed differently from its mass. The conventional definition of spin quantum number is S is equivalent to n on 2, where n can be any non-negative integer. Hence, the allowed values of S are 0, half 1, 3 on 2, 2, etc. The value of S for an elementary particle depends only on type of particle and cannot be altered in any known way, in contrast to the spin direction we will be seeing. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. Now we'll see you in the next episode of Cisco Educationals.